So this is topic 2.2, sorry, 2.1, the second half after the principle of superposition. In your workbook, this starts from page 117 to page 122, which will be covering electrical fields. So fields is idea that start from the idea that we had superposition of different charges. So in the previous lesson, we talked about how if you have, grab a pen. If you have a charge here that is say plus 1 coulomb, and you're gonna have another charge here that's minus 1 coulomb. Then for this one here, you're going to experience a pull in that direction. So that one will be direction of your force. And so basically, the idea of fields is that any charged particles is going to exert some form of work potential around them. So in the presence of this charge, this charge has potential to do work. Okay, so I'm just going to say that again. In the presence of this charge here, this charge here has a potential of doing work. So we're looking at not just working out the force between charges anymore. We're looking at what kind of potential they are to do work. Okay, so to illustrate this, I want to go to a simulation on PhET for Colorado, and this is one called charges and fields. So you should be able to get it from this link here. Okay, so um, now I'm going to represent. I'm going to start dragging a few charges around. Okay, so looking at this one here, okay, you start seeing some arrows around, and I'm going to put grid around too. So these arrows are vector arrows, which means if I put a positive charge around here, okay, if I put a positive charge around here, then it has potential of going in that direction. So if I put a positive charge there, it's gonna have potential of going outward that way, which makes sense. If I put a positive charge now here, okay, then as we expect, it's gonna repel from this one. Okay. Now as I move this positive charge around, you can see that the field line, these what we call field the vector arrows. If the vector arrows are going to move. Now what happens if I now put a negative charge around? Okay, so now if I grab this one and I now put it over here, you can see that some of the field lines are starting to change. So for example, on the top, in the middle here, the vector arrow is actually going almost horizontally. If I move this a little bit more, running away from me, if I put it flatter here, you can see that in general, I can, I can actually summarize this by saying this one's positive, this one's negative. I'm just going to wipe things out for the time being. And the field lines are going in that direction. I'm going to change color pen. Field lines are going in that direction. Now, what do these field lines actually mean? So this is saying that if I now put a positive charge over here, then the movement of this charge is actually going to go that way. Now, how can that be? Because the down a little bit. Now, if you ignore this one here, if you ignore the negative charge here, then the vector, the direction of the force experienced by this one here, it's going to go that way. And now, because of the principle of superposition, due to the negative charge now, okay, the second the vector due to this negative charge is going to go that way, which means if you combine the two together, then the vector sum is going to be horizontally in that direction. okay, which means for a positive charge here, imaginary charge over here, you're going to experience a force pushing it horizontally to the right. Okay, so in effect, field lines, the electrical field is a potential to do some work due to charges around them, and you can see that now. If I now put some, yeah, I'm going to reset this. If I now going to put some charges before, and this is one example we had before, you see that a charge in this direction here is going to be both repelled by this one here. Oh, it's going to be repelled by this one here, and it's going to be repelled by this one here, but it's going to be attracted by this one here. So in that case, it's going to go in that direction. Okay. All right. So so now that in the field is really in some ways independent from the charge, the actual magnitude of the charge, and I'll explain why that is in a second. Okay, so we should know that from this one here, all charges is going to exert some force around them. As you can imagine, the further away you are from the charge, the further away you are from the charge, then you're going to experience less field strength at that point. So what happens if you have now got 2 point sources that are of the same charge? Say you got positive charge there, positive charge there. And what happens if you're going to have a charge somewhere in between? So as you can see from the simulation over here, um, and if you have a positive charge here, okay, the results fairly predictable as we've seen before. Now, the overall field is going to be interfere if you have a second point charge. And I'm going to place it a bit closer so it's a bit easier to understand. Okay, so you can see that over here you're going to have repulsion force from both of these charges. So it's going to go that way, and it's going to go the other way. In between is a little bit trickier. If you have a point source there, and it's both being repelled by this one here and that point there, then it's going to go upward. That one's going to go downward. Okay, so and over here on this one here, it's a bit closer to this one compared to that one. So the so it's gonna have a much stronger vector from this one here, from this one here compared to that one there, and therefore you're gonna have a bit more you're gonna have stronger force going in the that direction. Okay, so how to represent this using field lines, and what we gotta do is to actually draw like this. Okay, so remember, the field lines is a direction, or um, the tangent of the field line is where the force is going to. Okay, so you're not, if you have something in the middle, okay, in the middle here, it's going to have equal force from the two of them. Now if you have something that's around here, it's going to go that way. Something that it's going to go that way. So overall, you're going to end up with field lines like this. On the outside, like on the right and on the left, you're going to have things feel like going this way and be more this way. So these field lines are really a crude representation of what you can see in the sim here. Okay, so the arrows is pointing in the tangential direction of these field lines here, and the field line is really denoting, well, if you got a chart over here, this is the direction it's going to go. Okay, and another thing that you should note is that the density of the field line generally denotes the field strength. Field strength, okay, is proportional to line density. Okay, so if I have something that's more dense, like if I draw a few more lines, okay, generally that means that it has a stronger electrical field strength. Okay, I mentioned a lot about field strength, and it's now time to be a little bit more analytical and a little bit more mathematical. So at this point here, I want you to think back on the gravitational constant. Okay, so Newton's gravitational constant is your g times by m1 times by m2 divided by r squared. Okay, and you should remember also that if we rearrange this, we end up having g equals to g m divided by r r squared. Okay, so the gravitation constant is not arbitrary 9.80 around the Earth. It's actually like acceleration constant for anywhere around the Earth. And I'll just let you recall that if this is the point source of um, point mass, then the field strength, okay, gravitational field strength, is always pointing towards the center of the mass. Okay, so this is now, you should probably have noticed that this formula is actually very similar to Coulomb's law. Coulomb's law states that F, which is the electrical charge or the force between the two charges, is 1 over 4 pi epsilon 0, being a constant, times by Q1, Q2 divided by the distance between two r squared. And I should note also that G here and this part here are constants, and which means M and your Q are similar quantity. One of them mass is, determines how much force you experience, and charge determines how much force you experience on electron that based on Coulomb's law. So is there a way of writing the some sort of constant which is base it so which is in another way of expressing force divided by mass? Okay, so G is saying that how much force you experience per mass. Okay, so and this is really a rearranged form of F equals to mg. Okay, so we're now trying to understand G a little bit differently. G is gravitational constant, is how much force you experience per mass. Okay, so we're linking those two together. Now, to express that with Coulomb's law, we have a new quantity, okay, and this time I'll call that E. Now, it's important to know that E is a vector because E is what you call um, electrical field strength. So electrical field strength is equals to your force divided by your charge